Well, hey everybody, welcome to another episode of Master the NEC, where we talk about the National Electrical Code. My name is Paul Abernathy, your host as always, and welcome to the video. Now, for years, I've been teaching people about a process of exam preparation and the importance of it. And again, one of the things that we have to understand about exam preparation, there's a philosophy behind it. And the philosophy of education for electrical exam preparation is that you really have to study with a plan. You really have to study with a purpose. And so as you start to dabble in the NEC, you're not going to be real successful if you're just flipping through the code book. You have to be going in there searching for things in order to really understand it. And that's what we built all of our platforms at Electrical Code Academy on, is the ability to systematically take you through the National Electrical Code, and along that journey teach you important things that you need to retain and remember and put into practice. Now, whether you're preparing for an exam or you're taking it into the real world, we have courses that are dedicated to both of those things, whether it's exam prep on our Fast Trax program, or you need to hone your skills on a residential, commercial, industrial, grounding and bonding. We have those programs too, all available at masterthenec.com. So check it out. And if you have any questions, you're always free to give us a call or actually email us or contact us from our contact page on our website in order to get more information on our programs. So what we want to talk about today is, from time to time in our Fast Trax program and with our students, they send us questions or ask questions about our Fast Trax program, and they ask me to break down the questions in a little more detail. So what we're going to do is we're going to put together a program here called Let's Ask Paul, and it's going to be based on 3 questions within our program that I can expand on and explain so that you can gain that knowledge. And what we'll try to do is educate you in a way that you can take the question, you analyze the question, which is what we call the actual process is ballistic training, whereas you actually hear it, I will read it, you can see it, you can follow along. All of that's based on how we do it in our program as well, because our programs can speak to you as well so that you can get all the senses going. But in this episode, we want to kind of answer some questions and be able to give a little more detail on each one of the questions being asked. So if you've got any questions, feel free to email them and contact us, and we'll be more than happy to possibly put them on a future episode of Let's Ask Paul. All right, so let's go on and get into the program. And so again, Let's Ask Paul. We're going to base it on the 2020 and some Q&A, and it's all, again, based on our Fast Trax program. So we'll make sure we cover the information. All right, so the very first question I get asked is, if a single rod, pipe, or plate grounding electrode has a resistance of blank or less, a supplemental grounding electrode shall not be required. Now, interesting thing to understand about grounding electrodes is that the National Electrical Code gives us 8 type of electrodes. So we have 250.52A1 through A8. And each one of them are unique. And the most unique is probably A8, which talks about things like underground metal tanks that might already be present on the premise. But everything's kind of got a logical flow. For example, A1 is dealing with water pipe grounds. Now, interesting is that water pipe grounds are not always have metal. It's plastic or something, PVC, not always metal. But if you do have a metal water pipe and it's in the ground in contact with the earth for 10 feet or more, then it can qualify as an electrode. And obviously, if it's there, you've got to use it. Now, you have other different types of electrodes. We'll look at each one of those really quickly so that you can have an understanding. But the question is dealing with single rod, pipe, and plate type of electrodes. Now, you are required to supplement a water pipe ground, because at some point they could change the water pipe line out and put plastic in. Now you've lost your grounding electrode system. So they require you to supplement it. Now it can be supplemented with any of the other electrodes, except you can't supplement it obviously with another water pipe ground. That wouldn't make sense. But you can use any of the others. Now the water pipe ground gets supplemented, but the other electrodes in our list that get supplemented is ground rods, pipes, and plates. Now, there is an exception to this rule that says, well, you don't have to supplement a ground rod, pipe, or plate, a single ground rod, pipe, or plate, if you can show a resistance of blank or less If you can do that, then you don't have to supplement it. So back in the day, we used to put in one ground rod. And if we couldn't show it was a specific ohms value, then we would put in a second one. So in the 2020 code, again, and it's been like this for 2 cycles or more, you have to put in 2, or you have to put in a single rod in some other electrode to supplement it, unless you can show that it was certain ohms value or less. And if you did, then you could just keep the 1, and that's all you would need. So I think most of us probably put in, if you're going to put a rod in anyway, most people probably put in 2 rods. Keep them 6 feet apart at minimum, and they're 8 feet long, and you drive them into the earth. If you hit rock, you're able to go to a 45. If you hit rock at a 45, then you're able to lay them horizontally in the ground. Now, supplementing the ground rods or pipes or plates is a supplemental requirement that only applies to rods, pipes, and plates. Okay, so let's go on and look at the code and kind of get an understanding of where this is coming from. So here's the National Electrical Code. This is the 2020 edition. And what we're going to see is that well, first things first, let's look at the rules here. So part 3 is where we're going to be. And you have the general requirement for grounding electrode systems right here in 250.50. And that's telling you that the grounding electrodes described in 250.52A1 through A7 that are present at a building or structure served shall be bonded together, all to form your grounding electrode system. So there's many of engineers who have maybe a concrete encased electrode, which is 250.52A3, and they might also require ground rods. Now, probably not necessary to have the ground rods because you don't have to supplement a concrete encased electrode. But if that's the engineer wants, okay, they have to be tied together. So you have different ones. So then that takes us to 250.52. And this is when it starts to talk about the different electrodes. Now, of course, you see the water pipe right here, and you see 10 feet or more in contact with the earth, then that would be an electrode. If it's there, you're required to use it, okay? And then, of course, you have what's called A2, which is a metal in ground, and that's kind of like, you've probably seen it's metal support like I-beam steel that's driven into the earth, or they're encased in concrete, either or, but it's 10 feet or more, either encased in concrete or in direct contact with the earth, and that would qualify as a grounding electrode. Of course, you have concrete encased electrodes, which again is basically rebar in contact with the earth inside of concrete, which is in contact with the earth. So the rebar is in the concrete, and then the concrete's in contact with the earth. And again, that is very common in construction. Now, one thing you'll notice is A1, A2, and A3, these 3 right here, these are pretty inherent to construction, right? The water pipe ground is something that's out of your control as the electrician. That's put in by the plumbing or the utility or whatnot coming to the building. We don't really control that. The in-ground support structure, that's all based on the construction of the building. We don't control that. As an electrician, I want to be keenly aware of that. Why? Because if that's already in place, then that makes my job a lot easier. I got to make a connection to it. But other than that, my grounding electrode system is done. Okay, so again, it can make my job easier. Now, when it comes to the third one, which is a concrete encased electrode, again, inherent with construction, not something me as an electrician is going to do. So it's going to be zinc galvanized or electrically conductive coated steel reinforcing bar or rod of not less than a ½ inch in diameter, installed in a continuous 20-foot length or in multiple pieces together comes up to 20 feet. And it's typically going, or we could actually have bare copper or 4 gauge that's in the actual concrete footer. And it's in contact with the earth through the concrete. Concrete's in contact with the earth. So that's inherent to construction. It's not something that me and you as an electrician are going to do, but we have to make that connection. So there's a timing thing. You got to make sure you're there in order to make that connection. Now, they could turn up a piece of rebar at the panel location. Everybody should have drawings at this point, and they know where the panels are going to go, and they can leave you that location to make that connection. And of course, that location where you make that connection has to be accessible, right? So that's all the stuff that we have to take into consideration, because that could be done prior to us even getting the project. Okay. Now, after you go through that, you get to what's called A4, A5, A6, A7, and A8. All of these used to be called man-made or something to do with the fact that we had to install them, right? It wasn't something that was inherently part of the construction of a building, right? So in this case right here, you have ground rings, you have rod and pipe electrodes, which kind of what we're talking about. And of course you see plate down here as well, okay? And again, you saw the mixture of rod, pipe, and plate, okay? And I'll show you where that comes in. All right, so you have all those, and of course, here's with your A8, other local underground system. Now, check with your AHJ here, because you might have an underground tank, but they don't feel comfortable as being that as an electrode to make a casing, to make a connection, or maybe a well casing. They can't see it. They don't know anything about it, so they're probably going to say, I don't know. You're not going to use that. But the others are all there for your use, and if they're all there, they all have to be tied together. Now, typically, I might see engineering drawings that have a concrete encased electrode, but they'll also supplement with ground rods. It's not necessary, but if the engineer calls for that, then you kind of do what they ask you to do, but again, not necessarily required from a minimum standpoint in the code, but they're just going above the minimum requirements, and that's okay too. They might have their reasons. They're the design people. Go with it, okay? Now, when we're talking about what we just said a minute ago, we want to talk about this, and that is 250-53A when it deals with rod, pipe, and plate electrodes. So very specific right here, and I don't know why I'm having highlighting issues, but there we go. It says rod, pipe, and plates shall be meet the requirements of 250-53A1 through A3. All right, so again, be installed below the permanent moisture level. I don't think I see people doing that all the time, but there you go. And then, of course, here's what we were talking about in our question. This is a supplemental electrode requirement. Notice it says a single rod, pipe, or plate electrode shall be supplemented by another electrode of the type specified in 250-52A2 through A8. Now, you notice A1's not here because you got to supplement a water pipe ground anyway, and you obviously can't supplement a single rod, pipe, or plate with the water pipe ground that could be removed in the future anyway. So you wouldn't do that, okay? So if you're going to do a single rod, pipe, or plate, and all you want to do is put one in, then you have to supplement it unless you meet the exception. Now, what's the exception? Now, the exception says if a single rod, pipe, or plate ground electrode has a resistance to earth of 25 ohms or less, which answers our question, the supplemental electrode shall not be required. Okay? So, anytime you're putting in a grounding electrode system that is going to be a rod, pipe, or plate, it's required to be supplemented unless you can apply the exception. And it's on you to be able to show the electrical inspector that it's 25 ohms resistance to earth or less. And you're not going to do that with a standard meter. You're not going to do that with a standard ohms meter. You need a clamp-on a ground resistance meter or a 3-point fall of potential setup to be able to do that. And usually, with the 3-point fall of potential, you have to have enough space to do it, okay? You have to space the probes out so far that go into the earth, and it can be very space restrictive. So a lot of people buy the clamp-ons, but they're really expensive. I would think it's probably just easier to go 6 feet away and install another ground rod. That's just me, but it seems like that would be the easiest way to do it. All right, so as you can see in our question, the answer is 25 ohms or less. But I think it's really interesting when you start looking at it, and that's why I tell people in our grounding and bonding course that we have, we really go over this in detail. I helped write some chapters in that book, and I'm proud of the document. And it also has our online course. And if you get the 2020 bundle program that we have going on right now, and I think we extended the $150 off discount, then you actually get access to all of our courses. And grounding and bonding, you can do it at your leisure. You get 2 years worth of access. So great program there. Okay. Next question. Paul, what size copper equipment grounding conductor is required for a circuit having a 40 ampere overcurrent device? Okay, a very common question. And the reason this comes up because you're going to see that when you're dealing with equipment grounding conductors, that there's a specific table in the code. Now you can go to the index. It's pretty easy to look up equipment grounding conductors. I like to tell people, if you're preparing for an exam, there's certain tables in the code that you just need to get familiar with. And that is equipment grounding conductors is 250.122, all right? And of course, along that journey, it's really important to understand things like 240.6a, which is the table for overcurrent devices, different things that you can kind of get familiar with. And of course, our Fast Trax program teaches you all the ins and outs structurally. We work you through the very beginning from boxes to box fill. Then we start moving to single family dwellings, multifamily dwellings, commercial. It's all done for a reason. Okay. So this is one of the questions in the program. So we want to go back to the code, and we're going to say it's a 40 amp overcurrent device and it's equipment grounding conductor. So here we are. Now, of course, what we're going to do is we'll go to the top, and we know that we're in 250, and you could go to the index. Or if you're savvy and you know that 250.122 is dealing with equipment grounding conductors. And I'll just kind of scroll on down here. Oh, incidentally, don't get confused, because 250.66 is dealing with grounding electrode conductors, okay? That's what that's all about, so not where we want to be. And you go down and you'll see that there's a 250.102C1. That's also not where we want to be, because that's dealing with the grounding conductor, main bonding jumpers, system bonding jumpers, supply side bonding jumper. Great table. Great table. It came to us 2 cycles ago. We used to refer you back to 250.66, which was a bit misleading, because that table was for grounding electrode conductors. But yet we were sending you there dealing with grounded conductors, bonding jumpers. Beautiful thing, a couple cycles ago, created table 250.102C1. It gives you guidance now. So again, watch my other videos. I have some other videos that talk about how to use each one of these tables. All right, so let's continue our journey. And we'll go to 250.122. So here's 250.122 for sizing equipment grounding conductors. A lot of information, how to increase the size when you have things like voltage drop, or if an engineer requires you to increase the size of the ungrounded conductors for whatever reason. They don't have to have a reason, but if they increase them, then you have to increase proportionally the size of the equipment grounded conductor. We have a video on that as well. It's a simple formula. And of course, a bunch of information, paralleling applications, multi-conductor cables were run in parallels and things like that. But here's what we want to look at. This is the table. This is a minimum size. Now, this is a minimum. Could it be larger? Absolutely. Is it required to be? Absolutely not. But when we say minimum, when an engineer increases the size of the ungrounded conductors, thus increasing the size of the equipment grounded conductor, then it's being sized above the minimum. And so, therefore, it's based on the rules in 250.122b for increasing the size. Doesn't change that we start with a minimum value. Now, the reason we want to bring this up down here is you'll notice that a 40 amp device does not appear here at all. So a lot of people get confused about this table. So it's a great question, especially for the student, is that you'll notice that 30 ampere device and a 40 ampere device and a 50 ampere device doesn't appear here. It's 15, 20, and then it jumps all the way up to 60. Now, why is that? Because anytime you have a blank in there from the next available size, so you have a 20, so the next one up, 25, 30, 40, 50, all of those are going to require you to jump up to 60. And so it would be a 10. Okay? So to answer that question, if it was a 40 amp overcurrent device, 40 amps does not appear here because it falls in that window between 20 and 60. You always jump up to the next size. So in this case, 30, 40, and 50, all are going to fall under the 60, and it's going to be a 10 gauge copper. Okay, so we go back to the question. What size copper equipment grounded conductor for this 40 ampere overcurrent device? 10 gauge copper. Just that simple. Just remember that just because your overcurrent devices are missing from the list, you know that you go to the next size of overcurrent that is in that list. Okay. All right. Next question is a blank is an electrical source other than services having no direct connection to circuit conductors of any other electrical source other than those established by grounding and bonding connections. Great question. And I get a lot of people that send me stuff and say, Paul, I need you to explain this in a little more detail. What are you talking about? How is this? Can this impact my installation? And I can tell you, as a person that's been involved in legal cases over improperly done systems, this one comes up a lot because it can really cause a problem if you're dealing with certain pieces of equipment. And I'll tell you what they are, but let's go to the code, because now this on an exam looks very much like a definition, okay? Or it's leading a definition. So what we want to go is see if we can find that. So let's go back to the code. And let's just kind of go to the top. And again, I'm using the 2020 edition online, in case you were wondering. And let's go down, and I know what we're looking for. And with a little practice, you will too. And we're going to look for, and I can find it. See if we actually have it here. And here we go. Separately derived systems. An electrical source other than a service having no direct connection to circuit conductors of any other electrical source other than those established by grounding and bonding connections. Okay? So let's talk a little bit about what a separately derived system is. So for basic understanding, let's talk transformers. Now, I don't know where you're at in your studies, but you've heard about step-up, step-down transformers. You've heard about things called auto transformers, things like that. Now, an auto transformer is not a separately derived system, okay? So it's not two separate winding. There's two taps on the same winding. But we're talking about transformers like a step-up or step-down, where you have a primary and you have a secondary, which reminds me, you want to learn about transformers and the code and secondary conductors and things like that, we have a 6-part video free over on our channel. Just go over to our youtube.com/Master the NEC channel, go to the playlists, and you will find our transformer videos, okay? And they were put out over a year ago, so you'll have to search for them. Unless you go to the playlist, then you can find them. Watch each one of them, because we build on it from piece to piece to piece. And that's important, because you need to understand how to take the values of a transformer and find out what the amps are so that we can apply it for conductor sizing and overcurrent protection of the transformer. All of that's critical steps that you have to follow. So it's a great series. Go check it out over on our website. Now, a separately derived system, say a transformer, you come into the transformer, you have what's called a primary side. And then you have what's called a secondary side. So those windings are very close, but they have turns ratio, whereas there's a number of turns relative to the primary to the secondary. Okay? Like if it was 100 turns on the primary and 25 on the secondary, that'd be 4-to-1 turns ratio. Okay, so again, you understand that the transformer is taking one voltage and changing it to another voltage, but they're not physically touching from primary to secondary. They're very close, but they're usually separated by dielectric material. Okay, so they're very close. They create magnetic coupling from primary to secondary, and when doing so, the grounding and bonding of the case and the equipment ground that's coming from the source, let's say a overcurrent device is coming in from your service, hitting a transformer primary, that you still have your grounding, you still have your bonding that you've got to do. So they are going to be intimate, but the primary to secondary are not. So it's literally two separate systems. And so that would be considered separately derived systems from primary to secondary. Now, let's talk about generators. So generators, where you have a generator that's outside, let's say it's a generator. It doesn't matter whether it's emergency. It doesn't matter whether it's legally required, or it doesn't matter whether it's optional. Typically, optionals are not going to be separately derived. But in many cases, emergency ones or legally required could be separately derived. Now, why is it important to know the difference? Well, all of this is based on the transfer switch. So if I have conductors coming from the generator and I have conductors coming from the utility, and they're coming to a transfer switch, if I have a switching mechanism, and again, the result is it's all feeding a panel. So if the generator's running, the transfer switch is in a position that feeds that panel. But if the utility's running, it's in a position to feed that panel. Okay? So we're transferring between the generator and the utility. Now, if I'm switching all the ungrounded conductors, that's the hots, and I'm also switching the ungrounded, generally a neutral, not always, but generally a neutral. If I'm switching all of them, then I have a separately derived system. It's two separate systems that are separated. They cannot come in direct contact. Now, we still have bonding. We still have all those requirements that will be intimate. We're talking about the ungrounded and grounding components. Now, if I have a transfer switch, which is typically what you're going to see in residential, is you have a solidly connected grounded terminal bus. So the grounded conductor from your generator and from your utility commonly connect on one common bus. So they are in direct contact. So they are not separately derived systems. Why is that important? Because you need to remember that if it's a separately derived system, because of full transfer and there's no direct connection, then you have to treat it as if it was kind of like a service, even though it's not a service. You have to treat it and establish grounding electrode system there and do everything a little bit different, okay? Otherwise, you can get circulating currents and create a hazard. Now, if it is not a separately derived system, then it is literally just another piece of equipment, just like, let's say, a range or HVAC unit. It's just another piece of equipment. And again, you have to treat it accordingly. So it's important to know, and you don't want to do things that you would do for a separately derived system to a non-separately derived system, because you can create a serious hazard. Okay? So it's important to understand whether or not you're dealing with this separately derived system or not. But the best way to remember is that there's no direct connection between, on a transformer, primary to secondary. On a generator, there's no direct connection between the feeders that are coming in from the generator and the utility lines that are coming into the transfer switch. They aren't intimate. Again, grounding and bonding, tying everything together, is going to be intimate, but the actual circuits are not. Okay? So, takes us back to our presentation a little bit. Hopefully you got that. So, a separately derived system is an electrical source other than a service. Remember, generators are not a service, okay? They are an electrical source, and those are feeders that are coming in from it, okay? So, great things to understand and learn in this program. We wanted to keep it pretty knowledge base, explaining the National Electrical Code and keeping it kind of to 3 questions. So hopefully you'll enjoy this series. You'll give us a thumbs up. You'll share with other people. Again, please feel free to contact us. Oh, contact information. You want to know where to get us? No problem. Let's go back real quick because I didn't do that. Is right here. Again, you can submit your questions, NEC questions, to info@masterthenec.com, as you see on the screen, and we will consider them for future episodes here at Let's Ask Paul at Electrical Code Academy. So again, hopefully you got something out of it. Look forward to another video soon where we will go over 3 more topics that people have submitted or that are part of our Fast Trax program. Till next time, folks, stay safe. God bless.